10-4 in Advanced Algebra 1. Last time we did measures of central tendency. That was like the mean, the median, and the mode, because they're all like in the center of the data. You know, that's why it's called central tendency. Today is measures of spread, also called measures of variability, like how spread out they are. And that's going to be the range, which is something that I think you've been trained in the past before to find the range. Don't you just take like the high minus the low, right? But the standard deviation is something that I'm going to take a guess that you have never seen before. True or false? Have we never seen the standard deviation? Heard of that phrase before at all? So standard deviation gets easier as you go. So it's the measures that, like, how typically you vary from the mean, right? It measures the typical distance in a distribution from a mean. And you're going to see some fancy symbols for it. For a sample, they use this S sub x for standard deviation. And for a population, they use this Greek letter right here, which is known as sigma. And you can hold all your sigma jokes, right, because it's not what it means. So I have an example for you, like just to kind of get it through. And as we do more and more examples, I hope standard deviation gets clear. So let's say I got Yolanda here. You don't have to write this down. We're just going to do it, right? Yolanda is a pitcher. She's pitched 5 games so far, and she's given up the following amounts of hits. In one game, she gave up 1 hit, and another game 2 hits, then 3 hits, 5 hits, and then 4 hits. So are you cool with this data right here? They say find the standard deviation. Well, here's how it works. We won't actually have to calculate it. We're going to let the applets do that. But if we don't see where it comes from, it's just like, I don't get what this number is all about. Like, what is this? So first thing you do is just find the average, right? So grab a calculator. I would like us to punch along with us. Let's find the average. Don't we need to add 1 plus 2 plus 3 plus 5 plus 4 together, right? And then divide it by what, since she's played 5 games? Divided by 5. What did you get? So 15 was the total, right? Divide that by 5. Isn't she giving up an average of 3 hits per game? Are we cool? We understand average pretty darn good, right? But then here's what we do. We want to see, I'm going to use not the proper vocabulary. I'm going to use like words that we understand instead. We want to see how far like each individual data point like deviates from the mean, right? So isn't one of the games that she like pitched in, she gave up 1 hit, right? So check this out. If I take this one value right here, this particular case, 1, and subtract away the mean, would you be okay with that? The mean was 3. Would you believe that we get like -2 in that spot, right? Isn't that mean in that particular game, she was 2 hits under her average in that case? She averaged like 3 hits per game, but she only gave up 1. So wasn't that 2 below the mean? That's how much it like varied from the mean, right? Well, because we got a negative value, and mathematicians are like, oh, the negative's going to mess stuff up. What they do is they take this number and they square it. Because if you take a negative number and square it, like won't it become positive in that case, right? So what would be -2 squared? 4. So if I do that again for all these other guys, right? If I did that for 2 hits, how do you feel about 2 minus 3 is -1? Are you with me on that? And then if I square it, I get a +1, and etc. 3 hits, she was right on her mean, right? You know, isn't 3 minus 3 0? When you square it, you get 0. 5-hit game, 2 hits over her mean, right, over the average. So I square it, I get 4. And then in this game where she gave up 4 hits, she was 1 over the mean. So if I square it, I get 1. You're kind of cool with what I did. I just see how it varied from the mean every single time, right? Sometimes it was 2 below, sometimes it was 1 below, sometimes it was 0. And then we squared all those numbers. Hey, could you do me a favor? Could we, like, add those up? I'll read them to you since it's all a mess right here. 4 plus 1 plus 0, which you probably don't have to type in, plus 4 plus 1. If we add up all these deviations squared, that's what those purple numbers are, how much did you get? 10, right? And then you would have to do this. So, like, the mathematicians are really smart. You would think, it's 10, yes, right? Okay. You would think that you would, like, divide that by 5 again, like just average those, right? But it doesn't quite work that way. You have to divide by 1 less term. Please trust that there is some serious math behind that, and there is some error because this is just a sample, not like the entire population. So there's some error, and they said, hey, we're going to divide that by, aren't there 5 games? We're going to divide that by 4. Could you punch that in your calculator? 10 divided by 4 is 2.5, right? But remember how these guys were squared, right? You know, so what do I have to do to get it back to normal? Since those are squared, what could I do? How do you get rid of a square? Square root. Take the square root of 2.5. Square root of 2.5, and you'll get a nasty number, right? Let's round that to 2 decimal places. Would you believe, you don't have to write it down, sorry, I remember we're just kind of going through this, that this is 1.58. That is what's called her standard deviation. And I put all of those numbers into an applet just to kind of show you. There's all her hits, graph like this. Can you see this SD? What does that stand for? Standard deviation. It means, on average, she is about 1.58 hits away from her mean in that case, right? And you can kind of see it right here. Here she was 2 hits below her mean, 1 hit below her mean, right on her mean, 2 hits above the mean, 1 hit above the mean in that case. So when you do all the math, the standard deviation was about 1.58, you know, like hits away from her mean in that case. It's kind of weird, right? But we'll dive more into that as we go through it. So, and then the last thing is the interquartile range. We'll talk a lot about that on the back side of this worksheet. It's the distance between the third and the first quartiles. Again, I like to do all the vocab up front. At least that's the way this textbook wanted it to do it, and then we'll go talk about it later. So we'll talk about interquartile range when we get to the back side. Let's just dive into it. Here was that same data we did last time. How long do these 20 randomly New York workers take to drive to work? You remember we did that last time, right? And it says find the range. Cool. How do you find the range? High minus low, right? What's the high in this bad boy? 85. Take away the low. What's the low? 5. Obviously, that is 80. Would you believe that the range of this data varies by 80 in this case? That's like the most typical measure of spread is the range. Do you think it is resistant? Would the range resist an outlier? Like would you feel that that could be a possible outlier? If we got rid of it, would it change the range drastically, or would it keep the range basically the same? What do you think? Change or the same? It would change drastically, so that's why the range is not resistant. Resistant means, hey, those extreme values won't affect you. Bro, an outlier is totally going to affect the range because isn't it either an extreme high or an extreme low? So that's the range. And then check this out. There is like 2 graphs on top of each other. It's kind of a weird one, right? So it's like, imagine there's another x-axis right here. You've got a graph in the green box, and then you got a graph in the orange box, if I could get that to work right here. You got 2 different graphs. Hey, where's the center of both of those graphs? 70.0, right? You know, what these graphs are is there's this like machine that makes nails. Do you know what nails are? You know, like hammer and nails, you know? It's like there's making these nails. And they measured how long they were in millimeters. So in machine A, like this one was 70, 70, 70, 70, 70. This one was 70.1 millimeters, 70.1. This one was 70.2, 69.9, 69.9, and 69.8. Do you kind of see what that data is all about? And then machine B, same dots, way different places. They say, look at how bad using the range could be to like explain the data. Do both of these machines have the same range? Is the high from the green machine the same as the high from the low machine? What's the high here? 70.2. What's the high here? 70.2. There's more of them, right? But isn't 70.2 the high of it, right? What's the low? Is it the same in both machines? So to find their range, right, I did that up above before I square rooted. I took 70.2 minus 69.8. You see that both of them have a range of 0.4, right? You know, both of them have a range of 0.4. So, and then are both of them centered at 70? So the parallel dot plots show the lengths of those nails. Both distributions are centered at 70.0 and have a range of 0.4 millimeters. But is this data the same? Like, which one do you think is making better nails more consistently? The nails are supposed to be 70 millimeters long. That's like what the requirement is. There's a little bit of tolerance. Which machine would you take the nails from if you were the one that had to sell these things? Which one's doing a better job? Machine A, because isn't it very consistently pumping out some 70.0s, and then there's a couple off. This one only had one of them that was 70.0, right? And the rest were off a bit. Even though they have the exact same range and the exact same center, there's very bits of different data in this, right? So you just got to watch out. The lengths of the nails made by machine blank vary more. That would be machine B. Don't they vary way more than of machine A? Like machine B is very inconsistent with how it is spitting out nails compared to machine A. So just because you have range, it doesn't mean it shows how things vary that well. So using the range is not a good idea a lot of times to describe something. Here's another one. They say 9 children were asked how many pets they had. They're like, hey, how many pets you got? Here's their responses, and then they put it into like a dot plot in this. So I'm not going to make you like copy and paste this data into an applet. Do you understand how to do that? Right? So you would go and copy and paste it. They say find the standard deviation. Boom. I did. I put it into the applet. What is the standard deviation? 2.55. And now here's the hard part. What does it mean? Right? We're still very new at it, and it's going to take a few examples. But it's like, hey, here's what it means. Like, on average, these kids like vary. The number of pets typically varies from the mean 2.55 pets. Yes, of course, we know you can't have decimally amounts of pets. It's just numerical data, right? So it's just one of those things. But the number of pets, whatever you're talking about, this thing was talking about number of pets. Here's the magic phrase, typically varies from the mean. Typically varies from the mean by whatever the number is. That's the standard deviation, which is still kind of hard to understand until we take it back to this. Here's Earl, and here's Kelly. Who's the better bowler? Well, now they tell us their standard deviations, just what you mentioned before this. This was the activity we did before class. Earl's scores have a standard deviation of about 40, while Kelly's is about 20. So talk to me. Somebody even said it. Who's the more consistent bowler, Earl or Kelly? How is her standard deviation, bigger or smaller than Earl's? Smaller, right? So here's what we'll do. They say describe each. Earl's standard deviation is 40. That means Earl typically scores within 40 pins from his mean. Within 40 pins from his mean, that's what Earl scores, right? So like, I don't know what his average is. Let's just say it's 150. You know, on any given day, he could score, I don't know, like a 190, you know, or a 110 or anything. He like typically scores within 40 pins. That's like total knockdowns, right, from his mean in that. Could you write a sentence to describe Kelly's with a neighbor? It's all about this. Earl's scores typically varied 40 pins from his mean. What is the standard deviation of 20 mean in that case? So talk it out with a neighbor, see what you think. Pause the video, give that a shot. It's pretty good, right? We took a moment in class. It's the same sentence over again. You just got to replace their names, right? You know, Kelly's scores typically varies 20 pins from her mean. Isn't Kelly more consistent? You know what you're going to get from that. It doesn't mean she's a better bowler, right? All it means is that you know what you're going to get from her a whole lot more than what Earl is. Earl is a wild cannon when it comes to bowling scores. He's all over the map, right? So the closer, like, the standard deviation is to 0, like, the more you realize this. Let's say you took 3 tests. First test, you got a 90. Second test, you got a 90. Third test, you got a 90. What's your average? 90. How much have you varied from your average on all of those tests? Nothing, right? Would you believe that if you use the statistics, you're like, it's kind of likely we're going to get a 90 on the next test, right? But what if you had test 1, 100, test 2, a 70, the next test, an 80, right? Do you see how you're varying more, you know? So your standard deviation, you're deviating more from an average. You find an average, and it's like, hey, man, I have a standard deviation that's a little bit bigger. There is no way that a standard deviation can be negative, right? The minimum it can be is 0 in that case. And that was because all of your data was consistent, just like the 3 tests. I got a 90, I got a 90, I got a 90, because it's how far away are you on average from your mean, you know? And the bigger the standard deviation, the more variability. Just like Earl's bowling scores. He had a standard deviation of 40. He's all over the place. Kelly was 20. Her data is closer together in that. So it takes a while to get used to standard deviation. It is weird. If you have questions about it, please, please, please ask. And then the last thing of the day is quartiles. Hey, if I say quart, what number should string into your mind? 4. So a quartile is just splitting the data into 4 even spots right here. So here's some data on the amount of fat grams in 9 different McDonald's fish and chicken sandwiches, listed from least to greatest. Here's how you would do it by hand. There are 9 of them. Which term would be in the middle, right? I want to find the median first, because if I got to split it into 4 equal spots, the first thing I'm going to do is cut it in half, right? You know, so which one would be in the middle? The 21, right? Isn't that right in the middle? That's the median because there's 4 pink numbers to the left of it and 4 blue numbers to the right of it. So you might kind of draw these little boxes that I'm going to do. I just cut it in half, right? Found the median. But if I want to split it into quarters, would you believe I cut each half in half again, right? So the weird part is I can't use the orange box anymore. He's out. I got to look at these pink numbers, and would you believe here in pink, there are 4 numbers in there. Isn't this right in the middle of it, right? Which is kind of different now because there's an even number. So what I have to do is average those. If you take 17 plus 19 and divide it by 2, you would get 18 back on that. That's called the first quartile, which is abbreviated Q1. Should be a capital Q also, right? The first quartile. That would be these guys right here. Then the second quartile is like right here in pink. And then to do it again, you just split those guys in half, right? So if you average 26 and 28, what would you get back on that? 27, right? That would be the third quartile in that situation. And it splits the data into 4 roughly equal spots. It's not always perfect because you see how it's like, okay, well, we had 2 things in this green section, and then there's kind of like 3 things in this section, and kind of like 3 things in this section, and then 2 things in that section. But it split it into fourths, right? Wouldn't you do that? You'd cut something in half, and then you cut those in half again, right? And you cut it into 4 equal sections. So they say find the inner quartile range. The inner quartile range is Q3, let's write that down, minus Q1. Range is just high minus low. And would you believe that those quartiles, Q3 and Q1, are on the inside, right? They're the inner quartile range. So Q3 is 27, and Q1 is 18. So there's our inner quartile range. If we just punch that in, that would be 9 in this case. And you don't have to do those by hand either. If you can see, here is like, I'll go to this data right here. Here is that same bit of data. Do you see in the summary statistics, there's our Q3 of 27 and our Q1 of 18. We'll learn so much more next time about what these quartiles do for us, right? But today it's just an introduction. Find the like inner quartile range. So you can put it into the applets, and you just take Q3 minus Q1. Why don't you do it the other way around? Why don't you do Q1 minus Q3? It would be negative, right? So, cool. So here's some questions coming up. Hey, do you think the inner quartile range is resistance? What do you think? Would it change the inner quartile range a lot? I mean, it's probably going to change, but would it change a lot? Or if I added another number like 50 to it, will it change the inner quartile range? Does the median change that much when we add or cut off a big value? Why not? Because the median's in the middle. What do you think about the inner quartile range? Is it resistant to outliers? Yes. I mean, it's true. The inner quartile range is going to change a little bit. Like the numbers are going to change, but it's not going to change drastically. Does that make sense? So that guy is resistant. So the inner quartile range is resistance. And what does this mean? When they ask you that on homework, this is the range of the middle half of the data. That's the range of the middle half of the data. That's the interquartile range. Why would you even want to do it? If you have bad data, or skewed data, I should say. So here's the real point of the lesson. When do you use the median? When do you use the interquartile range? When do you use the mean? When do you use the standard deviation? You use these, the median and the interquartile range. Are you cool? I didn't show you that abbreviation, IQR, interquartile range, is when the data is skewed and you got some outliers. Because these guys are resistant. You might want to write that down. These guys resist those outliers. The median and the interquartile range resist the outliers. So that's why we would use those. When we use the mean and the standard deviation, it's better for fairly symmetric or roughly symmetric that doesn't have outliers. Do roughly symmetric that doesn't have any outliers. So it's still back to the same story as last time. If the data is skewed, we're going to use the median. But now that we have a different measure, because that was a measure of central tendency, now that we have measures of spread, we will also use the IQR as opposed to the range. Like they say, don't use the range because that outlier is affecting it too much. Use the interquartile range. So let's do two quick ones. This is just multiple choice. 5 adult males were asked their shoe size. The results were these numbers right here. Find the standard deviation and interpret its value. You don't actually have to find it. They're just like saying this. This S of X is the standard deviation. Read through those choices with a neighbor. Which one of those multiple choices means what the standard deviation does? You're welcome to flip back and forth on the worksheet to other questions. Is standard deviation the same thing as the average? Or is there a different word for that? What word means average? So it's not A, right? It's not the average. Is standard deviation the range of the middle 50%? Or has that got a different name? What's the range of the middle 50% called? That's the interquartile range, so it's not that. It's one of these, too. And they're very close. So look back to what we did, especially with the Earl and Kelly. I'm not going to go back slide. How did we write that sentence with the Earl and the Kelly about what standard deviation means? What's the magic phrase besides Earl and Kelly and bowling and 40 and 20? What's the magic phrase? Typically varies from what? The mean. Because, like, is it every man asked the shoe size was this away from the mean? Or the shoe size for each male asked was typically varied from the mean? B or C? Yeah, it's just the ones they asked. It's not every man in the United States about their shoe size. And then here's a good one. I know we're getting a little tired. I feel you. Hang in there. Rick has taken 12 quizzes. His average, 83. And a standard deviation of 6. Talk to a neighbor first. What does that mean? He has a standard deviation of 6. His average is an 83. And he's got a standard deviation of 6. What's that mean to you? Here's my question. Is it likely on his next quiz he gets an 89? Is it likely? Where did I get the number 89 from? 83 plus 6, right? Because what if he scored a 77? Is that kind of likely on his next quiz? Because the standard deviation means he's going to typically vary this far from his mean, right? Isn't he got a mean of 83? So he's typically going to be off 6-ish, you know, from his score. Oh, God, he got 100 on the next score. Is that normal for his standard deviation or out of the norm? Out of the norm. That's a lot more than 6 above his mean. You know what I'm saying? So how's that going to affect the standard deviation? Let's make it easier. 90 on the first test, 90 on the next test, 90 on the next test, 0 on the next test. What's going to happen? Will the deviation change or will it get like tighter? It's going to get like way change, right? So isn't this standard deviation going to change, right? How will it change? How was this 100 in relation to his average? Was it above it or was it below it? So shouldn't his deviation like go up, right? It should go up in that case. So it will be greater than 6. The score of 100 is what? Either very far or very close to his average. Very far from his average. And it would deviate much greater than 6 or not at all. What do you want? greater than 6. This will increase or decrease the standard deviation. This will increase. So even if he scored below it, you can fire up to homework, that's fine. Even if he scored below it by a lot, it's still going to increase your deviation. The only way it's going to decrease the deviation is if you score really close to your average. Like if you got an 84. It's like, isn't he only 1 off from his average in that case, right? So the closer you get to the average, then that's going to make your standard deviation get smaller in that case. Cool.